Welcome to the deep dive. Ever just, stopped and wondered how everything around us actually holds together? Like the chair you're sitting on, the air, this device you're listening on, it all comes down to atoms. Today we're going deep. We're taking a look at a really great chapter from Organic Chemistry for Dummies, second ed. And our mission, basically, is to become atom mechanics. We'll dissect them, figure out their parts, see where those electrons actually live, and then the really cool part, see how they bond together, how they form the molecules that make up, well, everything, especially in organic chemistry.
Yeah, and this isn't just like theory for theory's sake, understanding where electrons are, how they behave, how atoms connect. It's absolutely foundational. It really is. It's kind of the ultimate shortcut to getting how molecules react and why they have the properties they do. It's looking at the very essence of matter.
So get ready. We're going to explore electron apartments, the different kinds of bonds, how greedy some atoms are, and even how all this tiny stuff determines the big 3D shapes of molecules. All right, let's dive in. Let's unpack the atom itself. What is it that really defines an atom's identity?
Fundamentally, it's the number of protons in the nucleus. That's its atomic number. Simple as that.
Right. So carbon, which is, everywhere in organic chemistry, has 6 protons. So its atomic number is 6.
Exactly. And for an atom to be neutral, charge-wise, it needs the same number of electrons, those negative charges, to balance the positive protons. But things get interesting when that electron count changes. If it gains or loses electrons, it's not neutral anymore. It becomes an ion.
Ah, okay. So gain electrons, you get more negative charge.
Yep.
That's an anion.
Yep, an anion. And if it loses electrons, it becomes positively charged. That's a conjugation.
Makes sense. Okay, so where are these electrons actually hanging out? Not in the nucleus, right?
No, definitely not. They're outside the nucleus in what we call shells. Think of them like concentric energy levels, kind of like layers of an onion, but for energy.
Okay, layers. So the first shell, the one closest in, holds 2 electrons.
Holds up to 2, yeah. The second shell holds up to 8. The third gets bigger, holds up to 18.
And the further out the shell, the higher the energy.
Exactly. Higher shell number, further from the nucleus, higher energy.
Now, I remember reading about shells and orbitals. Are they the same thing?
Ah, good question. No, they're related but different. The shell gives you the general energy level, like the floor in an apartment building. The orbital is the actual apartment on that floor, the specific region of space within that shell where you're most likely to find the electron.
Okay, the specific apartment, and this is where it gets kind of weird, right, with quantum mechanics.
Yeah, this is the Heisenberg uncertainty principle bit.
Yeah.
You can't know exactly where an electron is and where it's going at the same instant. Fundamentally fuzzy.
So no pinpointing its location,
Mm-hmm.
but we can know the region, the orbital.
Precisely. We know the probability map. We know the shape and location of the orbital, where the electron spends, say, 90% of its time. It's like house arrest, but for electrons in their orbital apartments.
And these apartments, these orbitals, they have shapes.
They do, and the shapes are super important for bonding. For organic chemistry, you mainly need to know 2 shapes. There are s orbitals, which are just spherical, like a ball.
Okay, spheres. And the other?
And p orbitals, which look kind of like dumbbells, or maybe 2 balloons tied together at the nucleus.
Dumbbells. Got it. And each orbital, s or p, can hold how many electrons?
Maximum of 2. But crucially, if there are 2 electrons in one orbital, they have to have opposite spins. Think of it like one spinning clockwise, the other counterclockwise.
Okay, and you mentioned p orbitals. Are
Yeah.
there different kinds?
Well, when you get to the second shell and higher, the p orbitals come in sets of 3. There's one oriented along the x-axis, px, one on the y-axis, pi, and one on the z-axis, pz. They all point 90 degrees from each other. And importantly, within the same shell, say the 2p level, all 3 of these p orbitals have the exact same energy. We call that degenerate.
Degenerate. Okay, so 3 p orbitals, each holding 2 electrons. Means a p level can hold 6 electrons total.
You got it. And we use notation like 1s, 2s, 2p, 3s, 3p to specify the shell and the orbital type.
So why all this focus on where the electrons are? How does that help chemists?
Because it predicts reactivity. Knowing the electron configuration, basically, the list of occupied orbitals for an atom in its lowest energy state, its ground state, tells you a lot about how it will behave chemically.
The ground state. So how do we figure that out? Is there a system?
Yep, there's a system. It's called the Aufbau principle. Aufbau is German for building up. You basically fill electrons into the orbitals, starting from the lowest energy one and working your way up.
Lowest energy first, like nature being lazy.
Pretty much. Nature prefers the lowest energy state. So you follow a specific order, usually shown in a chart. Ones first, then twos, then 2p, then threes, 3p, and so on.
Okay, fill from the bottom up.
Mm.
But what about those degenerate orbitals, like the 3p orbitals? If you only have, say, 2 electrons to put into the 2p orbitals, how do they arrange themselves?
Good point. That's where Hund's rule comes in. It says that electrons will go into separate degenerate orbitals first with the same spin before they start pairing up in any one orbital.
Why do they do that?
Because electrons repel each other. They're all negatively charged. It's more stable, lower energy to spread them out into different apartments on the same floor before forcing them to share one.
Okay. So let's try carbon again. 6 electrons.
Right. First two go in ones. That's 1s2.
Okay. Next 2 and 2. So 2s2, that's 4 electrons used.
Yep. 2 electrons left. They go into the 2p orbitals, but Hund's rule applies.
So 1 electron goes into, say, the 2px orbital.
And the next electron goes into the 2pi orbital with the same spin. The 2ps orbital stays empty for now.
So the configuration ends. 2p on 1, 2pi 1, not 2p by 2.
Exactly. That configuration is crucial for understanding why carbon forms 4 bonds, which we'll get to.
Okay, so we know where electrons live. Now, the big question. Why do atoms even bother bonding? Why not just stay separate?
Well, most atoms aren't actually stable on their own. They're kind of like, social creatures. They want to be like the cool kids on the block.
The cool kids.
The noble gases, helium, neon, argon, over there on the far right of the periodic table. They are incredibly stable, very unreactive. They've got it made, atomically speaking.
And what's their secret?
They have full outermost electron shells. That's the configuration jackpot maximum stability.
So other atoms want to be like them.
Desperately. Especially for the main group elements, there's a powerful drive to get 8 electrons in their outermost shell. That's a famous octet rule. Or 2 electrons for elements in the first row, like hydrogen, to be like helium. This desire drives almost all chemical bonding and reactions.
The octet rule, 8 is the magic number. And it's the outer electrons that matter for this, right?
Absolutely. We call those the valence electrons. They're the ones involved in the action in bonding. The inner electrons, the core electrons, they just kind of hang out. We mostly ignore them when talking about bonding. It's all about those valence electrons trying to get that full shell.
Okay, so how do they achieve this full shell? How do they bond?
There are basically 2 main ways, 2 extremes of bonding, ionic and covalent. And figuring out which type of bond you have is really key to understanding a molecule.
Let's start with ionic. You mentioned electron transfer earlier.
Exactly. Think about making table salt sodium chloride, NaCl. Sodium Na is in group 1. It has just 1 valence electron. Chlorine Cl is in group 17. It has 7 valence electrons.
Okay, so sodium needs to lose 1 electron to have a full inner shell, and chlorine needs to gain 1 to get 8 in its outer shell.
Perfect. So sodium gives this electron away completely to chlorine. It doesn't share, it just hands it over.
So sodium becomes Na plus but.
Right, a cation looking like neon electronically.
And chlorine becomes Cl.
An anion looking like argon.
Yeah.
Now you have this positive ion and this negative ion, and opposites attract, right? That strong electrostatic pull between them is the ionic bond. It's like magnets snapping together. Common in salts, non-metal compounds.
Okay, complete transfer. Got it. Now, what about the other extreme? Covalent?
Covalent is all about sharing. Think about hydrogen gas, H2. Each hydrogen atom has 1 electron, and it needs 1 more to fill its first shell, to be like helium.
But neither one is strong enough to just take the electron from the other.
Right. Neither is electronegative enough, which we'll get to. So instead of transferring, they compromise. They each put their 1 electron into the middle, and they share that pair of electrons.
So both electrons are attracted to both nuclei.
Exactly. That shared pair forms the covalent bond holding them together. Now, both hydrogens effectively feel like they have 2 electrons, like helium. It's kind of like a molecular cooperation.
Sharing versus stealing. Makes sense. So how do you know if atoms will share or steal?
That comes down to a property called electronegativity. It's basically a measure of how strongly an atom pulls bonding electrons towards itself. Think of it as electron greediness or piggishness.
Electron piggishness. I like that. Is there a trend?
Definitely. On the periodic table, electronegativity generally increases as you go up a group and across a period from left to right.
So the top right corner, fluorine.
Fluorine is the king, the most electronegative element there is. It's the biggest electron swine on the periodic table.
Okay, so you compare the electronegativity of the 2 atoms bonding.
Precisely. The difference in their electronegativity tells you the bond type. If the difference is basically zero, like between two identical atoms, HCl, they share perfectly equally. That's a pure covalent bond.
Okay. What if there's a small difference?
If the difference is, say, between about zero point 0.4 and 2.0, the sharing is unequal. One atom pulls the electrons a bit closer. That's a polar covalent bond, like an HCl or...
Polar, meaning it has poles like a little magnet.
Kind of, yeah. One end is slightly negative, the other slightly positive. We'll come back to that.
And if the difference is really big, greater than 2,
Then it's generally considered ionic. The more electronegative atom pulls so strongly, it essentially just takes the electron. Like in lithium fluoride, like EF, or potassium chloride, KCl.
Gotcha. And for organic chemistry with carbon, hydrogen, oxygen, nitrogen, the differences aren't usually that huge.
Exactly. Carbon and hydrogen are very similar. Carbon, nitrogen, oxygen, halogens. The differences are mostly in that polar covalent range. So organic molecules are primarily held together by covalent and polar covalent bonds. Lots of sharing, sometimes unequal sharing.
Okay, let's go back to that unequal sharing polar covalent bonds. You said one end is slightly negative, one slightly positive.
Right, because the more electronegative atom is hogging the electron density, this creates a separation of charge within the bond.
And that separation has a name.
It does. It's called a dipole moment. Understanding dipole moments is a really crucial skill for predicting reactivity later on.
Okay, so take HCl again. Chlorine's more electronegative.
Yep, so the electrons spend more time near the chlorine. We draw a little Greek delta minus symbol by the Cl to show it's partially negative.
And the hydrogen is left kind of electron poor. So
Right.
delta plus.
Perfect. Ill plus on the hydrogen. That little separation of charge, plus at one end, at the other, that's the dipole moment for the bond.
Is there a way to show that visually, like with an arrow?
There is. We use a special arrow, sometimes called a dipole vector. It has a little cross at the tail by the partially positive atom, and the arrowhead points towards the partially negative atom.
So the arrow shows the direction the electrons are being pulled.
Exactly. And the length of the arrow can represent how big the dipole is, how large the charge separation is, which depends on the electronegativity difference.
Okay, so predicting bond dipoles is just about knowing electronegativity trends.
Pretty much. Find the more electronegative atom, point the arrow towards it.
But what about the dipole for the whole molecule? Is it just adding up the bond dipoles?
Sort of. But you have to consider the molecule's 3D shape. It's vector addition. Take chloroform, CHCl3. Carbon is bonded to one hydrogen and 3 chlorines in a tetrahedral shape.
Okay, CH bond isn't very polar, but CCl bonds are definitely polar, with chlorine pulling electrons.
Right, so you have 3 CCl dipole vectors pointing outwards towards the chlorines. Even though it's tetrahedral, those 3 poles towards the chlorines don't cancel out. They add up to create an overall net dipole moment for the whole molecule, pointing generally towards the chlorine side.
Ah, so the shape matters. Can the bond dipoles ever cancel out completely?
Absolutely. The classic example is carbon dioxide, CO2. It's a linear molecule.
Oh, so
You're
yeah.
up. Bye.
The HCl bond is very polar. Oxygen is much more electronegative than carbon, so electrons are pulled towards the oxygens.
Right. You have one strong dipole pointing from C to the left, oxygen, and another equally strong dipole pointing from C to the right, oxygen.
They're equal and opposite.
Exactly. They perfectly cancel each other out, like a tug of war where both sides pull equally hard. So even though the bonds are polar, the CO2 molecule has 0 net dipole moment. It's nonpolar overall.
Wow. Okay, so that really shows how critical the molecule's shape, its geometry is. How do we predict that shape?
That brings us to VSEPR theory. It sounds complicated, but the idea is simple. VSEPR stands for valence shell electron pair repulsion.
Electron pair repulsion, so electrons push each other away.
That's the core idea. Electron pairs, whether they're in bonds or they're lone pairs just sitting on the atom, are all clouds of negative charge, and like charges repel. So they arrange themselves around a central atom to get as far apart from each other as possible to minimize that repulsion.
Makes sense, like people trying to avoid bumping into each other in a crowded room.
Kind of like that, yeah. And this repulsion leads to predictable shapes. If an atom has just 2 electron groups around it, like 2 single bonds or a double and a single, etc., they'll get furthest apart by being 180 degrees from each other. That's linear geometry. Think BH2.
Okay, 180 degrees, linear. What about 3 groups?
3 groups will spread out to 120 degrees apart in a flat triangle shape. We call that trigonal planar, like BH3.
120 degrees, trigonal planar. And the big one for carbon, 4 groups.
4 groups arrange themselves in a 3-dimensional shape called a tetrahedron. The angle between any two groups is 109.5 degrees. Methane, CH4, is the perfect example. Those are the main three geometries you need for organic chemistry.
Linear, trigonal, planar, tetrahedral. Got it.
Right.
But wait, you said earlier carbon's p orbitals are at 90 degrees. How does it make bonds at 109.5 degrees in methane?
Now we get to one of the cleverest tricks in chemistry. Hybridization. Carbon needs to make 4 bonds to get its octet, and VSEPR says those bonds want to be 109.5 degrees apart for minimum repulsion. But its starting orbitals, 1s and 3p's, aren't set up that way.
So what does it do?
It does a 2-step shuffle. First, a small energy cost. It promotes 1 electron from the filled 2s orbital up into the empty 2p's s orbital. Now it has 4 orbitals, 2s, 2px, 2p pi, 2t's s's, each with 1 electron, ready to make 4 bonds.
Okay, step 1, promotion. But the angles are still wrong.
Exactly. Step 2 is the magic. Hybridization. Carbon mixes that 1,2's orbital and those 3 2p orbitals together mathematically. It averages them out.
Mixes them, like mixing paint colors.
That's a great analogy. It takes these 4 different orbitals and blends them to create 4 brand new identical orbitals, and these new orbitals are called sp3 hybridized orbitals.
sp3, because it mixed 1s and 3p orbitals.
Precisely. And the amazing thing is, these 4 sp3 orbitals naturally point towards the corners of a tetrahedron exactly 109.5 degrees apart. Problem solved. Carbon uses these sp3 orbitals to form its 4 single bonds in methane.
Wow, okay. So it reshuffles its orbitals to get the right geometry. Does this happen for the other shapes too, like trigonal planar?
Yep. If an atom needs to make 3 groups around it, like in a double bond needing 120-degree angles, it mixes its 1s orbital with only 2 of its p orbitals.
So that would be sp2 hybridization.
You got it. It makes 3 identical sp2 hybrid orbitals that lie in a plane at 120 degrees to each other. And what happens to the 3rd p orbital?
It wasn't mixed.
Right. It remains as an unhybridized p orbital, sticking straight up and down, perpendicular to the sp2 plane. And that p orbital is crucial for forming double bonds.
Ah, okay. And for the linear case, 2 groups, 180 degrees.
Then it mixes the s orbital with just 1 p orbital. That gives 2 identical sp hybridized orbitals pointing 180 degrees apart. And now there are 2 unhybridized p orbitals left over, perpendicular to the bond axis and to each other. Those are needed for triple bonds.
Okay, CP3 for tetrahedral, SP2 for trigonal planar, SP4 linear. That makes sense. Is there an easy way to figure out the hybridization?
Usually, yes. Just count the number of things attached to the atom, other atoms, plus any lone pairs of electrons. We call these groups or substituents. 4 groups means sp3 hybridization, roughly 109.5 degree angles. 3 groups means sp2, roughly 120 degrees. 2 groups means p2, roughly 180 degrees. It's a pretty reliable shortcut.
Simple enough. And you mentioned hydrogen doesn't hybridize.
Right. Hydrogen only has that 1s orbital to begin with, so there's nothing for it to mix. It always uses its plain 1s orbital for bonding.
Okay, so we have these atoms with their fancy hybrid orbitals pointing in the right directions. How do they actually form the bonds? You mentioned overlap.
Yes. Covalent bonds form when atomic orbitals overlap, allowing electrons to be shared between the 2 nuclei. And there are 2 main types of overlap, leading to 2 types of covalent bonds, sigma and pi.
Sigma and pi. Greek letters. Okay, what's a sigma bond?
A sigma bond symbolized by SORMs when orbitals overlap directly end to end, right along the imaginary line connecting the 2 nuclei. Think of it as a head-on collision or overlap.
Head-on overlap. Okay, what kind of orbitals do this?
Lots. 2 s orbitals overlapping, like in H2, an s orbital overlapping with a hybrid orbital, like the CH bonds in methane, sp3s, or 2 hybrid orbitals overlapping end-on, like the CC bond in ethane, sp3sp3. The key thing is, all single bonds are sigma bonds. They form the basic framework, the skeleton of the molecule.
All single bonds are sigma bonds.
Yeah.
Got it. So what's a pi bond?
A pi bond, symbolized by forms from the side-by-side overlap of unhybridized p orbitals. Remember those p orbitals we left over in sp2 and sp hybridization?
Yeah, the ones sticking up and down.
Those ones. When 2 atoms with these unhybridized p orbitals are close enough, those p orbitals can overlap above and below the line connecting the nuclei. It's a sideways overlap, not head-on.
Sideways overlap above and below. So there's no overlap directly between the nuclei.
Correct. There's actually a node, a region of 0 electron density right along the bond axis for a pi bond. The electron density is concentrated in 2 lobes, one above and one below the sigma bond framework.
Interesting. So where do we find pi bonds?
Only in multiple bonds. A double bond always consists of 1 sigma bond from hybrid orbital overlap and 1 pi bond from side-by-side p orbital overlap.
1 sigma, 1 pi, and a double bond. What about a triple bond?
A triple bond is one sigma bond plus two pi bonds. Remember, speed hybridization leaves two unhybridized p orbitals. They overlap side by side in two different planes.
Okay, so multiple bonds have this extra pi component. Does that make them different?
Absolutely. Pi bonds are generally weaker and more reactive than sigma bonds. Those electrons sitting out there above and below the bond axis are more exposed and accessible for chemical reactions.
So we can actually picture how these orbitals combine, like draw a diagram.
Yes, drawing the orbital diagram of a molecule, showing which orbitals overlap to form each bond, is incredibly useful for understanding its structure and reactivity. Let's quickly try ethylene, C2H4. It has a CpC double bond.
Okay, ethylene. Each carbon is bonded to two hydrogens and the other carbon. That's three groups.
Right.
So sp2 hybridized.
Exactly. Each carbon is sp2 hybridized. That means each carbon has three sp2 orbitals at 120 degrees and one unhybridized p orbital. Hydrogens just have their ones.
Okay, let's picture the overlaps. The
Yeah.
CH bonds must be sigma bonds, right? sp2 from carbon overlapping with ones from hydrogen.
Perfect. Four CH sigma bonds. Now, the CH double bond, what's that made of?
Well, double bonds are one sigma and one pi. So the sigma bond must be from the sp2 orbital to one carbon overlapping head-on with an sp2 orbital from the other carbon.
You nailed it. An sp2 sigma bond between the carbons. That forms the main connection.
And the pi bond. That must be the unhybridized p orbitals.
Overlapping side by side. The p orbital on one carbon overlaps with the p orbital on the other carbon above and below the sigma bond. That's your pi bond, completing the double bond.
Wow, so drawing that out really shows you where the different types of electron density are.
Exactly, and it highlights that the pi bond electrons are kind of out there, which is why double bonds often react first in many chemical reactions. It's a direct visual link between structure and reactivity.
And there you have it. We've gone from protons defining an atom to electrons and shells and these weirdly shaped orbitals, all the way through why atoms bond, trying to be like those stable noble gases, right?
Right, that octet rule drive.
We saw how they can steal electrons in ionic bonds or share them in covalent bonds, and how that sharing isn't always equal because of electronegativity leading to dipoles.
And how those dipoles in the molecule's shape determine overall polarity.
And then VSEPR telling us the shapes based on electron repulsion, leading to carbon's clever hybridization trick to get the right bond angles.
sp3, sp2 mixing orbitals to match the geometry.
And finally, seeing how those orbitals actually overlap head-on for strong sigma bonds and sideways for those reactive pi bonds and double and triple bonds. We've really built molecules from the ground up.
We really have, and, it just scratches the surface, but it shows how profoundly the location and overlap of electrons dictate pretty much everything about a molecule. Its shape, its properties, how it interacts. Think about it. Plastics, drugs, fuels, their function relies entirely on these precise atomic arrangements and the resulting reactivity, all governed by these fundamental rules we've talked about. It really makes you wonder what other complex behaviors we see in the world might just boil down to simple rules of electrons repelling and sharing.
That's a fantastic thought to end on. Thank you so much for joining us on this deep dive into the absolute fundamentals of organic chemistry. Keep asking questions, stay curious, and keep exploring.